Hi guys, thanks for tuning in. In this video, we're going to talk about divergence and rotation, also known as two-dimensional curl. Now, our main way of introducing divergence and rotation is to look back at the Gauss-Green formula, because as you remember, the Gauss-Green formula is a correspondence between a path integral along a closed curve, which is equal to a double integral over the interior that's enclosed by that closed curve. So with the proper interpretation, we can use this formula as a computational tool for measuring flow along or flow across, depending on the problem that we're doing. And you can kind of see that this is the case, right? If you look at the formula, you could see we have an m comma n that looks like a vector field. This formula was designed for vector fields all along. And again, our interpretation here is that the Gauss-Green formula is a set of choices. We get to choose whether we want to do a path integral along the boundary or a double integral over the interior. We just have to be a little bit careful. We do want to make sure that our vector field has no singularities contained within our closed curve. So you do want a closed curve, and you do want to make sure that there aren't any singularities in your vector field contained within that closed curve, and then you should be good to go. So now that we have the Gauss-Green formula available to us, it's not a lot of work to apply that formula to a path integral, to the formula that we knew from last chapter for computing flow along. So here's three different ways of computing or representing the path integral that computes the net flow of a vector field along a closed curve. The one that we used most frequently was the integral of field dot tangent, but we also had this guy in the middle here, the integral of mx prime plus n y prime, and then also the integral of m dx plus n dy. The expression in the middle, though, this basically looks like the left-hand side of the Gauss-Green formula. So we can just invoke the Gauss-Green formula immediately and get that the net flow of a vector field along a closed curve can also be computed as the double integral of dn dx minus dm dy. We can either accumulate along the boundary with a single integral, with a path integral, or we could double integrate over the interior. And this is such a special expression here that we actually give a name to this integrand. We're going to call it the rotation of the vector field. It's not Rot field, but rather the rotation of the vector field, and it's the scalar quantity dn dx minus dm dy. And in higher dimensions, this is going to be related to a quantity called the curl, which in 3D is going to be a vector quantity, but in 2 dimensions, we're working with a scalar quantity here. We'll talk about that a little bit more later. I just want to mention the word curl now so that when it comes up in a later chapter, you've at least heard that terminology before. And now we can write that the net flow of a vector field along a closed curve is the double integral of the rotation of the vector field. And that's going to work as long as we have no singularities in our region R. So to summarize, we're going to take the exact same stuff from the previous slide and just write it a little bit more nicely. The Gauss-Green formula gives us a set of choices. To compute the net flow of a vector field along a closed curve, we can either choose to do a path integral along the boundary or a double integral over the interior. And that will be equal as long as we don't have any singularities inside of our curve. And then in Mathematica, if you wanted to compute the rotation of a vector field, you could define that using Mathematica's derivative notation. So the derivative of n of xy with respect to x minus the derivative of m of xy with respect to y. And now that we have this definition for the rotation of the vector field, we can actually update our gradient test that we had from last chapter. Remember, the gradient test really asked us to do two things. The main thing was to make sure that dn dx is equal to dm dy, but if you subtract dm dy from both sides, you get dn dx minus dm dy is equal to 0. Oh, and that's the rotation of the vector field. So we can actually update our gradient test to say that the rotation of the vector field should equal 0. And then the second part here, not technically part of the gradient test, but to make sure we have a conservative gradient field, to make sure we have a vector field that has all of the cool properties of a gradient field, we'd also check that we don't have any singularities on our interior region. So that's the other important thing. Now we can repeat the same process with flow across. So you take your path integral that you have for flow across. We have three different ways of representing it: the integral of field dot normal, or the integral of negative n x prime plus m y prime, or the integral of negative n dx plus m dy. It doesn't matter how you represent it. If you plug that into the Gauss-Green formula, you get that another way of computing flow across is to compute the double integral of dm dx plus dn dy. And this integrand here of dm dx plus dn dy is such a special quantity that we do give it a name. Again, we call it the divergence of the vector fields. Now, if you want to figure out where this dm dx plus dn dy comes from, you would plug negative n and plot positive m into the Gauss-Green formula, where you treat this negative n as your first component of your vector field, and this m as your second component of your vector field. So if you think of this as negative n of xy, comma m of xy, if you plug this first component where you would normally have m, and this second component where you normally have n, that's going to give you this double integral that you have right here. And that means that we can compute the net flow of a vector field across a closed curve by computing the double integral of the divergence over our enclosed region R. And again, this does depend on not having any singularities in your region R. So again, here a quick summary. This is the Gauss-Green formula applied to flow across. We can either choose to do the path integral along the boundary for field dot normal, or we could do a double integral of the divergence over the interior region that the closed curve encloses. Now, divergence in Mathematica would be the derivative of m of xy with respect to x plus the derivative of n of xy with respect to y. All right, and so why does it make sense to compute flow across using the Gauss-Green formula? Like, how is this a logical equality to have here? Algebraically, it makes sense, right? We could prove the Gauss-Green formula using our knowledge of calculus and the fundamental theorem of calculus. But intuitively, when we're thinking about measuring flow, why is this a logical equality? The main way that I usually explain it, and this is a rough analogy, so this is not going to be perfect, but we're measuring the amount of, say, fluid flowing across a boundary right here. And one way of thinking about it is that you could measure this in two different ways. Either you could look at your boundary, and at each point along the boundary put a little microcontroller, a little Arduino or a little Raspberry Pi sensor that senses fluid flow. And we can compute all of the fluid that's flowing across this boundary, and that should give us the net flow of this water across this closed curve, right? Whether there's more water flowing out or whether there's more water flowing in, we should get a pretty good measure of that either way by just setting up tons and tons of sensors along the boundary. And that's what your path integral does. Your other option is to do a little rate in, rate out problem, right? You look at the rate at which water is coming out of these sources, and you look at the rate at which water is flowing into these sinks, and you accumulate that, right? You accumulate that over the interior, and that net effect of that rate in, rate out problem, the accumulation of the divergence, should give you the same calculation. Now, if we want, we could try the same analogy again, but this time, say, with a bathtub. So instead of a fountain that has sinks and sources that are drains and water jets, now we've got a bathtub with only one sink and one source. Our source is where the water is flowing into our bathtub, and our sink is an open drain where the water is draining out of the bathtub. Now, unfortunately, in this rate in, rate out problem, the source is overpowering the sink because you could see that the water is overflowing the bathtub here. But if you wanted to compute how much you're flooding your bathroom, you could double integrate over the interior, right? You could double integrate and look at the rate at which water is flowing in and the rate at which water is flowing out, and that accumulation over the interior will tell you how much water you're flooding your bathroom with. Now you've got another choice. Gauss-Green says we can also accumulate along the boundary. So the other thing we could do is say, okay, let's go around the lip of this bathtub. And if we want to compute the net flow of our vector field along or across our closed curve, if we want to figure out how much fluid is flowing across our closed curve, instead, we could buy a bunch of little Arduino sensors or little Raspberry Pis, little microcontrollers, and set up, sample hundreds or thousands of points along the boundary here. And we could approximate this integral by accumulating all of the fluid flow across all of these little sensors. And that accumulation along the boundary will give you the same result. It'll tell you how much water you're flooding your bathroom with. Now, would this be a good thing to do? No. Probably turn off the water before you start doing math problems to figure out how badly you're flooding your house, but you get the idea. The Gauss-Green formula gives us a set of choices. We can either accumulate along the boundary or we can accumulate over the interior. So that ends this video, but thank you guys so much for tuning in. And in my next videos, I'm going to be showing you how to use the Gauss-Green formula to do some interesting flow along and flow across calculations.